Hello guys, how's it going? Guys and girls, people from all around the world. Now we are gonna continue with the third part of the embeddings course that we just started yesterday afternoon. I'm gonna check my audio here. Continue with the third part of the whole screen course that we just started yesterday afternoon. I'm gonna check my audio here. Continue. So let me just hear this is good. Let's just pause this because we don't need to have the feedback. Maybe at some point, but not now. And now we can continue with this course. Now we're in the third part. I mean, it's the second chapter, but I divided into two parts yesterday and today. Today we're gonna continue with this third part.
The final common embedding use case we'll discuss are classification tasks. Classification tasks can take different form, but generally they involve assigning labels to items. Common tasks include categorization, such as categorizing headlines into different topics, and sentiment analysis, such as classifying reviews as positive or negative. Embeddings can be used for both of these cases, utilizing the model's ability to capture semantic meaning. We'll be using a type of classification called zero-shot classification, which means that the classifications won't be based on labeled examples. Let's look at how that works with an example on classifying news articles by topic. First, we begin by embedding a description of each class label. Here, we'll use 4 classes: tech, science, sport, and business. We'll be embedding these labels and using them as reference points to base the classification on. Next, we embed the article to classify and calculate cosine distances to each embedded label. Finally, we assign the article the label with the smallest cosine distance. Let's do this in Python. Here are the topic classes we'll be categorizing with. In this example, we'll categorize using the label itself. So the first step is to extract the labels as a single list and use these as the class descriptions. Then embed each topic label using the create embeddings custom function that makes a call to the OpenAI embedding model. Here's the article we want to classify. The first step here is to combine the headline and keyword information into a single string that we can embed. We do this by defining a custom function that uses an f string to concatenate the headline and keywords inside a nicely formatted string. Finally, we can embed the text by calling create embeddings again, remembering to zero index the list returned so we have a single list of numbers. Now that we have the embeddings, it's time for the cosine distances calculations. This is a modified version of the find n closest custom function from earlier in the course, where instead of returning n results, we only want one, the nearest label. This means that instead of sorting by distance, we can find the minimum using the min function. Calling this function will return the distance and index of this label. Calling this function will return the distance and index of this label. Finally, we can use this index to subset the topics dictionary and extract the label. Printing the result returns the business label. Wait, that doesn't seem right. If we take another look at the article we're classifying, we can see that the headline indicates that the focus of the article is on tech. It's likely that the model captured the business keyword, which resulted in the mislabeling. The limitation in our approach that led to this was that the class descriptions lacked detail. The word business or tech doesn't contain much meaning on its own for the model to capture. So a better approach will be to use more detailed class descriptions. Let's try this again, but instead of using the labels as the descriptions, we use short descriptions to represent each class. The steps here are almost identical. We extract the descriptions in a single list, this time using the description key, and embed them. The rest of the code is the same. This time, when we print the result, we can see that the model classified correctly. Now, it's your turn to give this a try.
Got it. Okay. Embedding restaurant reviews. Okay, one common classification task that embeddings are great is for sentiment analysis. In this and in the following exercises, you will navigate through the workflow of performing sentiment analysis using embeddings. You've been provided with a small sample of restaurant reviews stored in reviews and sentiment labels stored in sentiments. So you'll use zero-shot classification to classify the sentiment of these reviews by embedding the reviews and class labels. Okay. So from the label sentiments and reviews using the create embeddings. So if you do the create embeddings, you will do it from the class descriptions, and then here you will do the it will be for label. How do you do this? The for here. Let's find here. Let's find the for. So it should be sentiment two dots label for sentiment in sentiments. Then you have the class descriptions here, so you will get an array of all of these positive, negative, and neutral. And here you have the reviews, so you will do the create embeddings of the reviews. So, but this just create the embeddings, right? And then I will need to iterate through each of these one to classify which one is the closest one, and then print the list. But this should make it. Yes, good. But just in case, I'm going to make the 12. Rename is gonna be 12. Embedding restaurant reviews. Just in case, I'm gonna delete all of these products and this one. I'm gonna find the closest. This one is gonna be not 3. Then instead of sorted, I'm just gonna return the mean, and I'm just gonna return this directly, which is going to return the just a dictionary with the distance and the indexed. And then when we need to create, well, so far we don't need this create product description, so we don't need to do this. The user history, we don't need to do this at all. Okay, so I'm just trying to get as minimum as possible for the distance we use for the cosine. I'm trying to get as minimum copied code from the previous one as possible, and then from here we need to get this, and then the just in case the sentiments and reviews we can get from here. So this is an array of dictionaries. This is an array of strings. The create embeddings, we got it already from the common file. Have the class descriptions, and from the reviews we have this. So far this should be safe containable already, but we're not gonna do nothing with it because we're gonna put here in the, oh no, all right. Wait 1 second. Let me do this. Here is my new code for the 12. The recommendation with user history. What I'm gonna do is I'm gonna do git status. This is an untracked file. Jesus. So I'm gonna save this 12. In this 11. The first thing that I modified here was the here, and no. So here it is. This original file. Hopefully we didn't modify nothing here. Rename. So yeah, it is a recommendation with user history. This is good, and now we are going to do the 12, which is the one that we were doing at the moment. And maybe I'm gonna did I modify anything to this file? No, it's gonna go the kit command, so better know. I'm just gonna run it, the Python 11, just to see that everything ran properly, because here I think that the last change was here adding 2 extra items to the to these 2 ones, so I should get recommended these 3 here. I'm just gonna check that that is correct, so it's good, so everything, nothing was modified there. Now let's close all of this. Let's go into the 12. So yeah, so far what it does is it finds just the closest, and we get the embeddings from the class and the embeddings, but that's nothing else. Now in the next exercise, probably we will do to find a classify and review sentiment. So now that you have calculated embeddings, you start to compute the cosine distances that extract the most similar label. You will do this by defining a function find closest, which is basically the same, but in enumerator embeddings, distance cosine, and this is the query vector, and here is the embedding. Return the mean. Here I enumerate reviews index, so we need to review embeddings. Here I should put the index, and here I should put the class embeddings, which is the list of the classes, and here we get to call the find the closest, which will return me indeed the closest one, and then the label, the class embeddings find the closest, that's the label, and the label should be the sentiments, and this should be the closest, and here I should get the index, which will get me the index, and here I should do the label from that. So this is gonna get me the index, so I'm gonna get the index that is from the sentiments, and then here I'm going to get the label from that element in that index. So that should be it, but what does it say? Label is not defined. But here in my previous one, it was here defined as okay. So maybe I'll just reload the page. Okay, it didn't save. Maybe it's good. I'll run. Yeah, the photos is positive. The server is a bit slow, but the photos is negative. The photos call really disappointing was clear negative. Yeah, that should be it. That should make it. Here I already defined this. It was just missing this part. So this I will put as here. And for enumerating reviews or in review embeddings, it will be both. Because here I can put reviews too. Review index class embedding find the closest. Yeah, this should be it. this should be rename 12 and 13. So this is gonna already tag me per each of the reviews. What is the sentiment detected? All right, that's good. Let's submit the answer. That's awesome. And now it says embedding more detailed descriptions. One of the last predicted labels didn't seem to be representative of the review. Okay, and I assume is this one that the service was a bit slow, but the food was good. This is not negative. This is not the positive. This is like neutral. So maybe to like when we're only embedding the class labels, standard descriptions of each class will be embedded instead. So now we're not embedding the label, but we're embedding the description. So because it gives more rich information about what we're describing. Understands that they're classified restaurants at the following are okay. So we should basically do the same, but in the class descriptions we should do class description, and here we should get description for class description in class descriptions. So this is how you iterate. Let me just check that I did it correctly here. For in sentence. Yeah, but here it's so I should do sentiment, I guess. It will be clearer. Sentiment, and I get the description will be the class description. Then the class embeddings will be the create embeddings of the class descriptions. Then we find the clauses of this. So this is okay. This is the same. Sentiments. Yeah, it's basically the same, but now we're just embedding this. So this should be good. Now we're just embedding the description here. So this should make it good. And now we're gonna make this like that 14. Embedding sentiment description, which basically will mean that we are doing the same as here, but we are basically we're doing the same here. The only thing that we're changing is that instead of here getting the label, we're getting the description, and then we're doing the same. So hopefully, because of that, because we're describing neutral as a neutral restaurant review, then when we run the Python 14, we will get the second review with a neutral label. So let's see what we got. Yeah, it's neutral now. Now it's more clear. So this is good. Let's continue. We finished the chapter 2 of embeddings. It's perfect, guys. Vector databases for embedding systems. Oh, it's getting more complex and interesting. So let's see.
Welcome back. In this chapter, you'll learn how to enable use cases with larger datasets by efficiently storing and querying vectors using a vector database. So far, we've created embeddings using the OpenAI API and stored them in memory. Because each embedding contains 1,536 float values, this results in around 13 kilobytes of data for each embedding, which becomes impractical to load for hundreds, thousands, or millions of embeddings. We also recalculated these embeddings with every query rather than storing them for later.
This is important. 13 kilobytes per embedding. It's small, but it's not really small, huh? Because if you already have like, let's say, 10 or 100. If you will have 100 embeddings, it will be already more or less like 1 megabyte. And 100 times 1000, more or less. So if you will have 100,000 embeddings, it will be already 1 gigabyte. So it will be like a lot to keep in memory.
To use. To compare similarity, we computed cosine distances for every embedded document and sorted the results, which are both slow processes that scale linearly. To enable embeddings applications with larger datasets in production, we need a better solution, vector databases. Here is a typical embedding application. The documents to query are embedded and stored in the vector database. A query is sent from the application interface, embedded, and used to query the embeddings in the database. This query can be a semantic search query or data to base recommendations on. Finally, these results are returned to the users via the application interface. Because the embedded documents are stored in the vector database, they don't have to be created with each query or stored in memory. Additionally, due to the architecture of the
If you query result and embeddings and the embedded small, embedded, okay.
database, the similarity calculation is computed much more efficiently. The majority of vector databases are what's called NoSQL databases, which contrast conventional SQL or relational databases.
The majority of databases are no SQL databases. Because normally I in most of my projects I'm using MongoDB, which is a non-SQL database. So maybe somehow it's already like structured there as a vector database, which will be really interesting. Don't use tables and can be structured in several different ways to enable faster querying.
SQL databases store data in tables with rows and columns. NoSQL databases don't use tables and can be structured in several different ways to enable faster querying. 3 examples of NoSQL architectures are shown, including key value, document, and graph databases. Vector databases aren't only used for storing the embeddings. The source text are also commonly stored. For vector databases that don't support this, source text must be stored in a separate database and referenced with an ID. Metadata is also stored in the database, including IDs, external references, and additional data that could be useful for filtering the query results. It could be tempting to store the source texts in the metadata, but this should be avoided. Metadata must be small to be practically useful. Adding a large amount of text data will greatly degrade performance.
Okay.
So what are the options when it comes to vector databases? Fortunately, there are plenty of options out there to suit almost every use case. Here are some of the most popular. When deciding which database solution to go with, there are several factors to consider. Vector databases can be managed, which is a turnkey solution that will take care of itself while you concentrate on application features. It does come at a price, but can be a sensible investment. Alternatively, you can self-manage and deploy your own server and database, either in the cloud or on-premise. This is usually cheaper, but requires time and expertise. Open source solutions provide greater flexibility in usage and can be more cost-effective if budgets are tight. In contrast, commercial solutions offer better support, more reliable performance, advanced features, and better regulatory compliance. We should also ask ourselves if our data lends itself to a particular database type. As discussed, there are several NoSQL architectures utilized by different database providers. Finally, does the use case depend on specific functionality, like embedding and storing both text and images for a multimodal application? In this course, we'll be using Chroma, as it's open source and quick to set up. At the end of this course, we'll provide resources for learning more about other solutions. Time for practice.
Okay. I guess here we're gonna use Chroma, but in the next course, because I already saw it in the next course, we're gonna use Pinecone, I think. Okay, to metadata and non-metadata. You have been hired by Filmflix to create a film recommendation engine using embeddings. The application will embed the film descriptions and store them in a vector database. Well, as an embed vector, I assume. Then use the similarity to the other films. Users like to recommend them new films. But first, you will need to decide how to structure the data in the vector database. So classify whether the information should be stored as a metadata in a vector database. Okay, so the release year should be metadata. The genre also metadata. The director that also there. Embed descriptions. This is not metadata. This is actually the embed. Reference ID to another table. This is metadata. Source descriptions. This is not metadata. It's perfect. Okay, choosing a vector database solution. Not all vector databases are made equally, and even more confusingly, what is best solution for one use may not be the best for another one. That's why it's so important to have a firm grasp on the vector database options out there and the requirements of the use case. A small AI startup could embed that AI are developing cutting-edge platform built on embeddings and vector databases. The platform is designed for organizations to embed and store large volumes of unstructured data, such as text, images, and audio files. They are looking for cost-effective, customizable so that experienced engineers can develop data maintained. Which features will their vector database? So it's a small startup cutting-edge platform. Because the platform is for organizations to embed and store large volumes of unstructured data, text, audio, images. Okay. So if it's a small startup and there is not too much budget, probably I will use open source and manage, because also like if they will need to manage, if they will do self-management, there will be like too much resources on that, like human resources, and it will probably not let the startup focus on feature development and market analysis and support multimodal storage. Okay, I need to understand, like in a new conversation. Okay, I need to ask what is multimodal storage in a vector database? Aha. So you store embeddings that are from different data types. So that means that, for example, you have an image and you embed it and you get a text. You have text and image into the same vector space. All right. Okay, that's good. So at least one answer is manage the other from more expensive than. I mean, yes, but I mean we can self-manage. But the thing is that, okay, this will all depend on the budget too. So okay, creating vector databases with ChromaDB. Time to start getting hands-on Chroma with ChromaDB. Okay,
Time to start getting hands-on with ChromaDB. Chroma comes in two flavors: a local mode where everything happens inside Python, and a client-server mode where a ChromaDB server is running in a separate process. Client-server mode requires running a separate process for the Chroma server and is better suited for production systems. We'll only be looking at local mode, which is the simplest way to run Chroma and is well suited for development and prototyping. In order to connect and query the database, we first need to create a client. We import ChromaDB and create a persistent client by calling persistent client. Persistent clients save the database files to disk at the path specified. To add embeddings to the database, we must first create a collection. Collections are analogous to tables, where we can create as many as we want to store our data. To create the collection, we use the createCollection method. When creating a collection, we need to pass the name of our collection, which is used as a reference, and the function for creating the embeddings. Here, we specify the open. So we do the Chroma tools open embedding function. So we create the collection here. We use the API key, and then we create the API embedding function and API key. In Chroma and in many other vector databases, a default embedding function is used automatically if one isn't specified. The list collections method lists all of the collections in the database, so we can verify that our collection was created successfully. We are now ready to add embeddings into the collection. We can do so with the collection.add method. In this example, we are adding a single document. Chroma will not automatically generate IDs for these documents, so they must be specified. Since the collection is already aware of the embedding function, it will embed the source text automatically using the function specified. So it will automatically embed the text that I'm passing. That's interesting. Most of the time, we'll insert multiple documents at once. So you will generate the IDs, and which we can do by passing multiple IDs and documents. After inserting documents, so it's abstracting the whole process that we were doing to embed the text. It was already abstracted. Collection.count will return the total number of documents in the collection, and collection.peak will return the first 10 items in the collection. As we can see, the embeddings were created automatically when we inserted the text. We can also retrieve particular items by their ID using the get method. In the following ID using the, we can also create it automatically in the text. We can also retrieve the first 10 items in the collection ID using the get method. In the following exercises, we'll insert a dataset of Netflix titles into the Chroma database. For each title, we'll embed a source text including the title, description, and categories. While this is not a massive dataset, we must not forget that each of these texts is going to be sent to the OpenAI embedding endpoint and therefore cost money. Before inserting a sizable dataset into a collection, it's important to get an idea of the cost. OpenAI provides the cost per 1,000 tokens on their model pricing page, which means we can find the total cost by multiplying this value by the number of tokens in the text we'll embed and dividing by 1,000. We can count these tokens with OpenAI's TickToken library. TickToken can convert any text into tokens. First, we use the encoding for model function to get a token encoder for the embedding model we're using. To calculate the total number of tokens, we use the following Pythonic code. This reads, for each text,
context for text. Yeah.
In documents, encode it using the encoder and take the length to obtain the number of token in the text. Finally, sum the results. This code is much more concise and efficient than looping through the documents. It just takes a little time to get used to if you're used to looping. Finally, we calculate the price by multiplying total tokens by cost per 1K tokens over 1,000 and print the result. We work with a smaller subset in the exercises of the first 1,000 titles. Now, it's your turn.
It's good. Okay, now getting started with ChromaDB. In the following exercises, you will use a vector database to embed any query. 1,000 fields and TV shows from Netflix dataset intros in the video. The goal will be to use this data to generate recommendations based on search query. To get started, you'll create a database and a collection to store data. So here, we'll just take a hint. Because okay, that process client say you can leave the file. So this is the name of the collection. I'm gonna use this OpenAI embedding function. Has been imported, and here I should pass the embedding function to the collection. Persistent client, and then client.collections. Give 1 second because I need to reload this page. Yep. And now here what I want to do is I want to run this. But I don't know what's going on, that is not loading. Okay, so the last time happened this and I don't want to just keep doing this without actually submitting because I really want to complete. So let's take a break. I'm gonna restart my computer and then we're gonna come back to this, okay? But just in case, I'm gonna database. I'm gonna do this here. I'm gonna copy this here just to have it saved, and then we're gonna come back later with the second part, okay? But it will be the third or fourth part, I don't know. I'll check it. But thank you guys. I'll come back in a 1 hour.